Hi everyone, I'm Dustin. This is ongoing unpublished work with my supervisor Mike and my summer student Fatima. And yeah, so we're going to talk about AI safety and robust planning. So what's the goal? Well, very broadly, we want to learn good decision-making policies. So this is kind of a control setting. And one obvious thing that this group would probably think of is, well, we should just do trial and error learning, reinforcement learning. But this has some problems, or this can be problematic in different situations. So it can be infeasible. It can be too slow or require too much experience. It could require expensive equipment or instruments. It could be dangerous. It could be dangerous to execute initially poor exploration policies and these kinds of things. So I'll give some specific examples of where this could be a problem. So for instance, giving medical treatment recommendations. Would be a matter of life and death. So we can't really explore different actions, these kinds of things. Another situation might be financial product recommendations. Maybe we're a bank and we want to suggest different products to clients. But maybe we're really sensitive to client turnover, and so we can't be really experiment extensively with our suggestion policy. Another situation is autonomous driving. Again, this is a matter of life and death. Training a car to drive from scratch with trial and error on open roads obviously isn't going to be feasible because it's going to be dangerous to all the other drivers and pedestrians, etc. Okay, so this is, we're restricting ourselves not to this kind of setting. But what can we do in this setting? Well, people do these kind of tasks. So that means we can get data from competent policies. Then we can use that data and think carefully about the problem and come up with a model. And then with that model, we could study it and do planning on it to come up with a good policy. Now, this also has major problems. And the one I'm going to focus on is limited model fidelity. So we have this data from the real world, but we're going to be building these models that are inherently limited because they're not going to be as complicated as the real world. And then the planning algorithm is going to overfit to these imperfections. So if we were to use the planned policy in the real world, now it's not going to look so good, even if it was optimal in the model, right? So we'll look at an example of this. But is all that motivation and setting clear? All right, great. OK, so I'm going to present a really, really simple contextual bandit setting to explain kind of the method I'm thinking about. So let's imagine we have one feature and the reward is on the y-axis. We have two different actions, blue and orange. We have two data points from blue. We have one from orange at different parts of the space. Now, regardless of what action we choose with whatever feature we see next, we're not going to get any information. We're not allowed any feedback. And now the question is, if we see the feature 1, which action should we take? So we have, and these points, there are no noise in the actions. So these points reflect the true reward of that action in that part of the space. So we have this guaranteed value that we would get by choosing orange, and then this uncertain value that we would get by choosing blue. So in order to compare them, we really have to have, oh, go ahead.
What is a contextual bandit?
OK, sorry. So by contextual bandit, I just mean that we're going to be given a feature. In general, we could be given a feature vector. And then we're going to produce a distribution over actions. And we're going to be evaluated on the expected reward from that policy and the reward function. Yeah. So we want to maximize our reward. Choose a policy that maximizes our reward, and it has to be given the feature. So given the feature value, we produce a policy, and we want to maximize that value. All right. So in order to compare blue and orange at a point in the space like 1, we need to have a belief about what the value of blue will be in that part of the space. And by belief, I just mean a probability distribution. So let's imagine one particular set of beliefs we could have. So we could believe there are 4 functions distributed according to these probabilities, and these are just all arbitrary. This is just an example of what we could believe the function looks like. But that's not going to be very realistic. Maybe let's think about something slightly more realistic and assume that the reward functions can't change too quickly. So now we have this diamond of possible rewards between the values that we know about. And the average value is just 1, because both of the points we've seen gives a reward of 1. And then the minimum is 0, and the maximum is 2. OK, but now how do we? Oh, yeah, go ahead.
So the function that you showed earlier, in that case as well, the reward was not changing very quickly. It was still smooth, right?
Oh, yeah, in the other case, they were smooth as well, but we only had a finite number of them, which is probably unrealistic. Like, usually we would consider a whole range of possible functions, right, that would be possible, right?
So this is the range.
Yeah, this is a continuous range of possible rewards. Right, and we could maybe assume that all of the rewards in this space within the diamond are equally likely. That might be reasonable. All right, so now which action are we going to pick if we have these beliefs? Well, it really depends on how our attitude towards risk. So if we're risk neutral, then we would just say, well, the blue action, it's more likely under this belief that our reward will be greater than the orange, that for the orange action, so we should choose the blue action. But if we're really risk averse, we're going to say, well, the minimum value that I could get for choosing the blue action is 0, which is a lot less than the orange action, so we should pick the orange action. And then there's a whole gradient in between. So this is the kind of robustness optimization, or these are the kind of robustness measures that I'm thinking about, or the robust policies that I'm thinking about here. We could think about a different kind of belief here, rather than just this diamond assuming that the function changes slowly. We could think about like a normal distribution. This is going to be more typical, right? This is a Gaussian process. So we have beliefs that expand outward as you get further away from the data in kind of a smooth way. And they go out infinitely far. So there's no function that's completely ruled out, but you have an area of higher probability. And each of these different colors represent another standard deviation away from the mean. So we might believe that it's more likely that the reward is closer to 1 and becomes less and less likely as it goes further away from 1. All right. So like I said, once we have these beliefs, we still need a way to characterize our attitude towards uncertainty. So now I'm going to talk about risk and robustness measures. Is everything clear so far? OK. Yep.
What is the y-coordinate of the orange dot?
The reward for taking the orange action.
But you don't know that.
You do know the orange action. You don't know the reward for the blue action at feature 1, in the middle.
Oh, OK. So there's just different reward functions.
Exactly. Yeah, we have an asymmetry between the knowledge that we have for the different actions in the space. That's the key thing here. All right. OK, so robustness measures. So what we're going to do to think about how the range of policies that we could have and how they would perform under different risk attitudes, we're going to take our uncertainty distribution, sample it a bunch of times. So that gives us a reward function, a set of reward functions. And we have our static policy pi here. We're going to evaluate that policy on all of the reward functions. So we're going to get a whole bunch of expected values. And then we're going to sort those and graph them. All right? And then we'll get a graph that looks like this. So on the x-axis is percentile. So these are just every point is another world that we could be in. It's another reward function that was sampled from our distribution. And the y-axis is the value that we got in that world with our fixed policy. Since this is sorted, it's always going to be increasing. And so this is really giving a complete characterization of how this policy will do under the distribution that we specified for the reward functions. All right? But in order to properly compare policies, we're going to need to summarize this in some way to get just a scalar value. So one obvious thing that you might think of is just to take the average value, right? The area under this curve. That's one thing you could do. Another thing you could do is you could take the areas under different percentiles, and this corresponds to a risk measure that's been well studied in econometrics called conditional value at risk. So on the left here we have where we're really interested in just the sliver at the end there, the height of the smallest or the hardest world for us. And this is going to be like very pessimistic, but very robust. And then over here, I have arbitrarily the 50th percentile, and this is just the area under that curve. And this is conditional value at risk for the 50th percentile. And so it's going to be somewhere in between, in terms of robustness, between this policy and, or this measure rather, and the average value measure that I mentioned before. It turns out that policies that optimize this type of family of robustness measures can be found by solving a game, a zero-sum imperfect information game to be specific. So that game looks like this. At the top of the game, we have chance sampling n reward functions from our belief distribution. We're going to have an antagonist choosing k of them. K and n are going to be parameters that are going to determine the exact robustness measure. And then chance will sample a single reward function. And then our protagonist is going to choose a policy. And the protagonist is not going to get to see which reward function was sampled. The protagonist has to choose the policy without seeing the specific reward function. And then the policy gets evaluated. So it's imperfect information because of this bit here, where we have an information set. But other than that, it's a fairly simple game. The antagonist, of course, is the policy is evaluated, and the protagonist gets that value. The antagonist gets the negative of that value. And this evaluation is just what we've already seen, where you sample a reward function, and then you get the expected value. All right. So if we could solve this game, find an equilibrium policy for the protagonist, we will have optimized the robustness measure that corresponds to the k and n parameters that we set. All right. Another thing maybe to give you some intuition, if we set n to be really large and k equal to 1, it means that chance is going to sample a whole bunch of reward functions, like a whole variety of them, and then the antagonist gets to choose the one that's worst for our policy. And so that's going to correspond to the 0th percentile optimization. And then when k is equal to n, the antagonist has no power, and so you're just really optimizing for the average value. And then setting k to be smaller than n is going to be somewhere in between. Yep.
Are both of these chance samples from the belief distribution?
So this one is from the belief distribution, and this one is uniform over the k selections from the antagonist. Thanks for that. Yep, Adam?
5 minutes left.
Thank you.
So once you have a reward function, why do you have multiple policies?
Oh, these are decision nodes. So this is the, they're just separate for us looking at the tree. But since, so I've drawn it as a dotted ellipse around here. That's to denote that the protagonist doesn't get to see which of those it's in. This is conventional notation in imperfect information games. All right, now to solve this game, I'm not going to go into too much depth because I don't have too much time, but the basic idea is it's like gradient descent. We're going to incrementally improve our policy over time. So we're going to start with an initial policy. We're going to evaluate it. This is the value that we get. It's the minimum because this is the antagonist, and then this is just the average value. Over the bottom part of that game. We're going to do some partial improvement step. And then as t goes to infinity, we're going to get closer and closer to an equilibrium policy. If you want to know the name, it's Monte Carlo regression regret matching. We can talk about it after if you want. Anyway, OK, so here's a full example. I have 3 minutes. That should be all right. So we have each action is going to get a random step function as its rewards. So this is what it looks like for the teal action. We're going to have a baseline of -10. And so the action is going to give a reward of -10, except in a few places marked here with stars, where the value is going to be near 0. We're going to have this for all 7 actions that we're going to use. And the trick is that we only get to see the data points that are greater than -10. We only get to see these good points to simulate as if our sampling policy is competent. In this case, extremely competent, like it's perfect in this world. Also these points are all deterministic, so no noise. And so then the data that we get to train on looks like this. So we have all these different actions in different colors. And they have values between -1 and less than 3. That'll make sense. All right, great. If you look at the optimal greedy policy, if you knew the full reward functions, it would look like this. So over the feature space on the x-axis, here we have the weight on that particular action, where the color corresponds to the action. So it plays the green action in this part of the space, the teal action in this part of the space, the orange one here, etc. That'll make sense? All right. So now we need our beliefs over the entire space. So we're going to do Gaussian process inference. We get a belief about the reward function for each action that looks like this. This is just showing a single action. So we get to see these data points. We don't get to see these data points. And we have this kind of belief. This is showing 2 standard deviations away. So we have certainty where we have points and uncertainty everywhere else. And if we just take the greedy policy with respect to the average function from those beliefs, we actually end up just playing the teal action, which ends up being really bad. So this graph on the right here shows the reward. We do really well in this space, but really poorly everywhere else compared to the optimal greedy policy that gets to cheat and see all the data. So can we do better than that? And it turns out that we can. So this is the percentile curve, kind of like what I showed before. Percentile on the x-axis, value up here on the y-axis. This graph here is the value compared to that bad greedy policy as a baseline. And we can see that both k of n, both 1 of 100 and 85 of 100 policies do a lot better in this part of the belief space. So when like around the 35 percentile, we do much better below that. Yeah, so right. And then this shows just the areas that each curve is optimizing. So the orange one is just the greedy policy. It's optimizing over the whole belief space. The 85 of 100 is optimizing for this area. And the 1 of 100 is optimizing for this height here. Okay. And what do they look like? So the 1 of 100 policy actually looks a lot like the optimal greedy policy. And the 85 of 100 looks kind of like in between that and the map greedy policy. And then on the real world, the optimal greedy policy gets this 1.72 value. 1 of 100 gets 0.96. Whereas the greedy with respect to the map got -7, so we improved a lot over that. And then the 85-100 is kind of in between again. And across the space, the value looks like this, kind of as you'd expect. Yeah, maybe I'll just skip that in since there's no time left. So takeaway messages. Robustness can make AI systems safer. Robust policies can be obtained by solving a game. This can be applied to offline contextual bandit settings. Thanks.
What's the next step?
Right. So actually, Fatima and I are working on, that's actually a good thing to show. If I can, oops. On a driving simulator. Here we go. OK, so this is a little driving grid world game that we made. There are bumps in the road and pedestrians, and you can speed up, and you can change lanes. And so like I said before, one setting was autonomous driving, where you might want to do this. And so we're thinking that if we should be able to use this to show how robustness can help in a sequential decision-making setting.
So you're going to formulate this as an MVP rather than a contextual bandit?
Yeah, that's right.
So then you will have a distribution over next state as well.
Yes. So, right. There are two things you could do.
You have a distribution of distributions over next state.
Right. So there are two things you could do. One, the one thing that we're going to do, which is easier, so if you just have a distribution over rewards, the problem is is a lot easier. It ends up being that you just want to do like basically the contextual bandit thing, or maybe more like a value iteration or TD kind of thing. Like the trick is that you have to evaluate your policy every time you want to sort those rewards, and you have to do that in every state. Right now, we're just thinking about tackling this as in a tabular way. So we remove a lot of the problems around function approximation. Yeah, and once you do that, then you're basically just doing value iteration, except you're choosing your reward function based on how well you do on different reward functions. In fact, the successor representation helps a lot, because once you get the successor representation, you can just apply it to a bunch of reward functions. And then that lets you sort the reward functions, and then you can improve your policy with that difficult set of reward functions. If instead you wanted to have uncertainty over transitions, then it gets actually a lot harder. And technically, you have to treat it as a game where you keep track of the history. And so you need non-stationary policies based on your history. Yep.
Sorry, I forgot. Can you remind me how you select the policy once you have a reward distribution?
Right. So once you have the reward distribution, actually, yeah, I'll go back to the slides here, if I can find them. Sorry. Oops. Sorry. 1 second. There we go. Okay. Right, so we have our reward distribution. Right, okay. So chance is going to sample n reward functions. The antagonist is going to choose the k worst for our current policy. Like we're going to set some current policy, and the antagonist gets to see it, essentially. And then we're going to be evaluated on those k reward functions and take the average value.
Sorry, the policy is chosen before the antagonist chooses the reward.
So we need to choose an initial policy. Yeah, that's right. So initially, our policy is just going to be uniform random.
Okay.
And then once we get a value from that, right, we're going to get this value, right? So assume we have some utility function over the policy given the reward function. So we get that value. We're going to make some partial improvement to the policy. And I didn't go into details about what that means because it's a little bit complicated. But it's basically doing gradient descent to improve the policy. You can think of it almost like policy gradient kind of things, almost. Yeah.
So, I thought before that the antagonist would choose like the worst reward functions under the best policy. So sort of choose the worst reward functions that have the lowest maximum reward or something.
Okay.
But since that's not the case,
Right.
So like the antagonist thinks that the agent's going to choose one policy, but the agent actually gets evaluated under a different policy. And those two policies can be very different.
Oh, sorry. So we set a policy. So if we just look at how this game is set up, we choose a policy, and then the antagonist knows what policy we're going to choose. Or rather, the antagonist could reason about all of the policies that we could choose, and then is allowed to choose the reward function.
The antagonist knows the algorithm that's choosing the policy.
Exactly, yeah. Yeah, so you really have to evaluate this given a policy. And then once that's chosen, the antagonist, their decision's easy because they just want the most reward. So they pick the worst ones. Yeah. Mm-hmm.
Can you maybe give me a high-level sense of previous work in this area, like other ways that you could do safe reinforcement learning?
Right. So there was a tea time talk last month on doing mean value optimization and they were doing in the full MDP doing a block coordinate descent method. So they were doing like in the full the real experience MDP setting, and yeah, that I don't quite know how to do, or even you wouldn't really want to do this, right? Because this is going to be pessimistic under uncertainty. We do have maybe some ideas of turning that around and thinking about, well, what if we're paranoid that there's some reward left somewhere in the space and being hidden from us? But we haven't kind of fleshed that out completely. If your uncertainties are all Gaussian, maybe it's restricted just to reward uncertainty. Or if you have, if you are allowed non-stationary transition functions, then things become a little bit easier. And I don't remember exactly the methods for doing it, but I remember that it was tractable. So there are specific situations where it's tractable. In general, though, when you have transition uncertainty and not in a particularly nice form. You're stuck doing a game kind of setup as far as I know. For reward uncertainty, it's not so bad because you can get away with essentially doing imperfect recall if you know that game terminology that lets you kind of get back to the original RL setting where you only deal with states rather than states and time or states and histories for your policies. Yeah. Right.
10 seconds left.
Oh, good timing, actually. All right, thanks, everyone. Yeah.